Hello! In this video, we are going to prove the following theorem. Let f and g be families of sets. Then, the union of f and g is equal to the union of f and the union of g if and only if, for all sets a in f and b in g, the intersection of a and b is a subset of the union of f and g. Now, if you recall, given a family of sets f, to say that x is an element of the union of f means that x is an element of some set in f. And previously, we have already shown that no matter what families of sets f and g are, well, this set is in fact a subset of this set. Okay, so now let's get into the proof. Now we're trying to prove a statement containing if and only if. So what we're going to do is we're going to prove if this is true, then this is true. And then we're going to prove if this is true, then this is true. Let's start out by proving if this is true, then this is true. And to do so, suppose this is true. Our goal from here is to show that this is true. And since we're trying to prove a statement about every set in f and every set in g, give me any set in f and any set in g. I'll call them a and b, respectively. And our goal with a and b is to show that the intersection of a and b is a subset of the union of f and g. So give me an arbitrary element of the intersection of a and b. I'll call it x. And with x, we want to show that x is an element of the union of f and g. Well, since x is an element of a and b, it follows that x is an element of a and x is an element of b. Well then, we see that x is an element of a set that is in f. So, this tells us that x must be an element of the union of f. But also, we see that x is an element of a set that is in g. So, x is an element of the union of g. So since x is an element of the union of f, and x is an element of the union of g, this tells us that x must be an element of this set. But since these two sets are equal, this means that they have exactly the same elements. So since x is an element of this set, this means that x must then be an element of this set. So putting this together, we started with an arbitrary element x in the intersection of a and b. And from there, we show that x must then be an element of the union of f and g. Since x is arbitrary, this means we have shown that everything in this set lies in this set. But now, since a and b were arbitrary sets in f and g respectively, this means for all sets a and f and b in g, we have that this is true, which is exactly what we wanted to show. So at this point, we have shown if this is true, then this is true. Now we're going to prove the converse. That is, we're going to show if this is true, then this is true. To do so, suppose that this is true. And our goal now is to show that these two sets are equal. And the way we're going to do that is we're going to show that this set is a subset of this set, and this set is a subset of this set. Well, we already know that this is true. So all that's left to show is that this set is a subset of this set. So give me an arbitrary element of this set. I'll call it y. Well then, y is an element of the union of f, and y is an element of the union of g. Since y is an element of the union of f, this means that y is an element of some set in f. I'll call it set S. Similarly, since y is an element of the union of g, this means that y is an element of some set in g. I'll call that set T. But now we can apply our hypothesis to S and T. Because if we take A to be S and B to be T, well then we have that the intersection of S and T is a subset of the union of F and G. And since y is an element of S and y is an element of T, we know that y is an element of the intersection of S and T. So since y is an element of the intersection of S and T, and everything in the intersection of S and T lies in the union of F and G, it follows that y must be an element of the union of F and G. So putting this together, we see that under the assumption y is an element of this set, it follows that y is an element of this set. Since y was arbitrary, this means that every element of this set also belongs to this set. So we have both inclusions, and that tells us that these two sets must be equal. So we have shown if this is true, then this is true. And we've proven both directions of the if and only if, so we have proven this entire statement. And that's exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.